Seagrass meadows are key engineering ecosystems, providing several ecological functions like nursery functions, habitat provisioning, primary production, and several ecosystem services as well, such as erosion control, food provisioning, water purification, and carbon sequestration, for instance. The temporal evolution of seagrass meadows in Arcacon Bay was studied between 1989 and 2019.
Le bassin d'Arcachon il est historiquement couvert par deux espèces d'herbiers austères qui ont plein de fonctions écologiques. Alors, c'est un habitat pour plein d'espèces, et notamment des espèces qui ont un intérêt halieutique important, comme la sèche. Elles agissent sur la dynamique hydrosédimentaire, donc elles permettent le maintien des sédiments, le maintien du trait de côte, mais aussi elles garantissent la transparence de l'eau, ce qui permet une meilleure production primaire du phytoplancton et donc une meilleure production ostréicole notamment, et des palourdes et autres qui sont pêchés.
The results show a severe decline over the last decades of both seagrass species. The total surface regression over the studied period is estimated to be 25.8 square kilometers for Zostera noltii and 2.7 square kilometers for Zostera marina, which represent declines of 33% and 74% respectively. Several factors have been identified as potential causes of the decline of those meadows. In particular, the heatwaves of 2003 and 2006, combined with the negative effect of contaminants. Mathis Cogna's thesis highlighted hydrodynamics as the main factor contributing to the regression of seagrass beds and as a major obstacle to their resilience. When seagrass beds regress, the speed of bottom currents increases, which can lead to the mechanical uprooting of nearby plants. In addition, this increase in current strength encourages erosion, leading to an increased concentration of suspended sediments. This accumulation of sediment reduces the availability of light, the main factor controlling plant growth. At the same time as the regression, the increase in water turbidity could have significantly reduced the amount of light reaching the plants, leading to an amplification of the regression through its own consequences on sediment dynamics. As a result, the seagrass beds lose their ability to reduce the bottom current, leading to an increased remobilization of sediment. This process further weakens the ecosystem and contributes to the observed collapse of the seagrass populations in the basin, which is known as a positive feedback loop. As part of the West Coast project, Seaboost aims to design, deploy, and test a large-scale solution to mitigate local hydrodynamic forces. The aim is to reproduce the effects of seagrass on its environment, to inverse this negative effect of the feedback loop, and create a context favorable to seagrass resilience. This is supposed to be achieved by mitigating flow velocities close to the bottom. During the project, we built a strong relationship with the local MPA manager, which is the Arcacon Bay Marine National Park, and built another project together in the same area to merge our approach that focuses on hydrodynamics with the introduction of biological material. Our intervention is based primarily on the deployment of a system that reproduces seagrass characteristics and mimics its effect on the local environment. It is divided into 3 phases. The first phase was a small-scale experimental phase aimed at testing and measuring the effect of different roselière configurations by varying the length of the strands, their density, and their position in the water column. This was done to define the most relevant deployment pattern to optimize the flow attenuation effects per surface unit. We selected an area with seagrass meadows under regression and performed several tests and measures. Then we defined with a numerical model a settlement pattern that would be able to tackle both flood and ebb current effects and to optimize bed shear stress. During a second phase of deployment, we settled our system at large scale to restore more than 1 hectare of seagrass meadows and to assess the effect of different deployment patterns. The whole operation was settled in September 2023. The settlement involved a team of more than 20 people, including the Seaboost team, the local MPA team, oyster farmers, and an NGO team. Several sites were equipped to assess both the effects of the experimentation within and outside of the settlement pattern, and to assess how we could benefit from the wake of the system. Finally, a third phase will include basin-wide modeling of long-term seagrass restoration strategies to feed into the local management strategy for marine ecosystems. Several monitoring studies were performed to test the ability of the solution to create a favorable context and restore seagrass meadows.
Alors on va réaliser différents types de suivis. On aura des suivis biologiques, donc pour suivre la biologie qui est l'objectif en fait de cette restauration, qui est vraiment de faire revenir les herbiers. Et à côté, on va avoir différents suivis pour avoir des intermédiaires qui va être l'effet hydrodynamique. Donc ça, c'est l'effet sur les courants. Est-ce que ça ralentit vraiment les courants? Est-ce que ça ralentit vraiment les vagues? Et puis ensuite, on a tout l'effet de ces courants et des vagues qui vont avoir un effet sur le sédiment. Donc le sédiment, en fait, c'est des transports, on appelle ça la morphologie, morphodynamique. Et en fait, c'est des bosses, des creux qui sont créés par les systèmes. Et en fait, ces bosses, ces creux vont aussi avoir un impact sur l'hydrodynamique. Donc en fait, on a plusieurs boucles de rétrocontrôle. Et donc là, l'objectif, c'est de suivre à la fois l'hydro, la morpho et la biologie.
Moreover, we also performed in situ monitoring. This served the purpose to characterize the performance of the Arcacon Basin seagrass meadows to perform climate regulation service, meaning the ability to trap and store greenhouse gases. This involved several samples on different sites to assess carbon content and greenhouse gas kinetics, associated with isotope analysis to perform a dating of the carbon stored in the sediment. We are then able to estimate the stock and the dynamics of carbon for that kind of ecosystem in order to build realistic strategies. This work was performed jointly with the Aegis Environment Team and the INRAE Lyon laboratory. In parallel, Aegis Water and Maritime team worked on setting up coupled hydro-morpho-ecological models for risk assessment, which included erosion, submersion, and water quality that are all related to the ecosystem restoration at the pilot site. A model in which the ecosystem services of the potential restoration areas must be considered and quantified by adapting them to the current climatic conditions and future scenarios. Furthermore, our research indicates that restoring vegetation in the Arcacon Bay could reduce sediment deposition and enhance secondary channel erosion, leading to improved hydrodynamics. In collaboration with Ifremer, a prominent French marine ecology laboratory, we employ the Mars model, which is a large-scale, high-resolution tool to analyze the progression and regression trends of seagrass meadows based on various environmental factors. By simulating basin-scale strategies, we aim to inform local stakeholders with strategy workshops, optimize seagrass restoration efforts, and adjust a large-scale seagrass restoration strategy in the Arcacon Bay. The first results are very promising, as we can demonstrate a positive effect on the seagrass feedback process through our method of equipping the channel sites. This should allow to restore seagrass that is situated nearby, thus allowing to reduce flow velocities on large foreshore areas and enabling seagrass recovery from near to nearby. We have strategies allowing the restoration of several dozen hectares over time, thanks to the equipment of the channel sites on long lines surrounding the foreshores that are in strong regression.